According to legend, when Albert Einstein met Charlie Chaplin, he said to him, "You will become a great man. In your films, you stay silent, yet everyone understands you." Chaplin replied, "I admire you even more. No one in the world understands your theory of relativity, but you still became a great man." It's not known for sure whether such a conversation actually took place, but it's easy to agree with it. Einstein's theory of relativity is one of the most profound and difficult things to understand that the human mind has ever created. It provides answers to many of the most important questions about motion, space, and time. But is it perfect? No. There are also paradoxes in the theory of relativity, and one of them is the so-called twin paradox. And to figure it out, we'll have to travel into space and come back. Are you ready? Let's go. So let's imagine two twins. Let's say their names are Tolya and Kolya. By fate, Tolya became a cosmonaut, and he has to go on a journey to a distant star. Kolya, on the other hand, has to wait for his brother's return on Earth. Both brothers have ultra-precise atomic clocks, which they synchronize before the flight. Any good story needs an unexpected twist, and it really does happen. When Tolya returns to Earth, it turns out that his clock is behind Kolya's, and as a result, he is now younger than his twin brother. Surprising? Yes, but only if you're unfamiliar with the theory of relativity. So, how is it even possible that a cosmonaut making an intergalactic flight could age less than his brother who stayed on Earth and end up younger than him? The thing is, time isn't the same for everyone. It's relative and flows differently for those moving at different speeds. The faster an object moves, the slower time passes for it. You can easily feel this relativity, for example, when you're riding on a train and your train meets another one rushing toward you on the adjacent track. At that moment, you clearly feel that you are standing still, and only the other train is moving, and at a tremendous speed. But there are people in the other train as well, and for them, it's you who are rushing past with a roar while they are standing still. This is where we come to the twins paradox. Due to relativity, the astronaut feels stationary while Earth appears to move away from him. We've seen this more than once in science fiction movies, and that's actually how it is. Remember our train. When you're riding in it, you're sitting or lying still, and it's the scenery outside the window that's moving relative to you. You yourself are stationary. So, if the astronaut is stationary and the world moves around him, does that mean he should be the one to age? After all, the person who stayed on Earth was moving while the astronaut was standing still. But then when both brothers meet, it would turn out that each of them has become older than the other. But that's absurd. This is exactly what the so-called twin paradox is about, which at one time gave Einstein quite a headache and was actively used by critics of his theory. But is it really a paradox? As we mentioned earlier, one of the main principles of the theory of relativity states that the faster an object moves, the more time slows down for it, and this has been proven many times. Moreover, the experiment with two clocks was actually conducted only on Earth. Atomic clocks placed on board a supersonic aircraft showed a tiny delay in time compared to the synchronized clocks left on the ground. But on Earth, the delay is purely symbolic in magnitude and we can't feel it. Will Tolya be able to end up younger than Kolya even if he spends years in the sky at supersonic speeds? But what about in space, where we're talking about completely different scales of distance and speed? The twin paradox has several interpretations and explanations. One of them involves the acceleration that a rocket develops in space. One of the brothers, Tolya, experiences acceleration as he travels through vast cosmic distances, while the other brother, Kolya, is in a stationary system, that is, on Earth. At the same time, for each brother, time does not flow in any special way. Tolya, while experiencing acceleration and his time slowing down, does not notice it. The brothers can only feel the difference relative to each other. Are we confusing you too much already? Hold on. After all, this is far from the only interpretation of the paradox, and some believe that acceleration has nothing to do with it. Let's do another thought experiment in the spirit of Einstein. Let's imagine there are three observers in constant motion and none of them is accelerating. Let's call them A, B, and V. Observer A is at rest on Earth and Observer B is moving toward a distant star at a constant speed without acceleration. Observer V is moving toward the same star from the opposite side, coming from another planet. which is at the same distance from the star as Earth. Observer A sees V moving away and V approaching. But even though A is firmly standing on the stationary Earth, all three will be moving relative to each other at a constant speed. How can you equate something stationary and something moving? Here you can use the relativity equation to get the following formula. Time in motion will be equal to stationary time divided by gamma. Gamma is universally used in the theory of relativity as an indicator of the speed ratio between two observers, and it is always greater than or equal to 1. By using this equation, we will see that the time experienced by two moving observers will pass faster than for someone who is on Earth. There you have a mathematical proof of ephemeral matters, but haven't you ever felt this yourself? A person in motion will actually feel that not much time has passed compared to someone who was at rest. But how does this happen? It's not about acceleration at all. We've already come to this conclusion using a thought experiment. Returning to our observers, we can take into account that observer A is in a stationary frame of reference. Observers B and V arrive in different frames, B in the receding frame, V in the approaching frame. But which of the observers would we put at the center of consideration? For each, the other two are, one moving away, one approaching, meaning they're in two frames of reference simultaneously. That's exactly how relativity works. The world looks different for everyone. If we go beyond this setup and add a fourth observer, G, who watches the movement of A, B, and V from the outside, we'll see that for G, observer A still has a single, constant speed, while B and V have two different speeds, which was already proven by the formula above. But what about acceleration? After all, there was no acceleration in our experiment. Does that mean it doesn't play a significant role? Yes, only one thing matters. We are comparing the time experienced by a person in one frame with the time experienced in two frames. The acceleration, which is obviously necessary for a person to travel between stars, is a random factor here. Only time, distance, and speed matter. So how did you like our little journey into the complex yet very fascinating world of time and space? Perhaps this immersion has raised more questions than it answered, but that's the thorny path of science, and we are happy to be your guides along it. The speed of light is about 299,792,458 meters per second. That's a pretty precise value, isn't it? But how did we arrive at it? According to the calculations of Olaf Römer, the speed of light is 220,000 kilometers per second. Half a century later, in 1728, the discovery of aberration allowed James Bradley to confirm the finiteness of the speed of light and refine its estimate. The value obtained by Bradley was 308,000 kilometers per second. The most accurate measurement of the speed of light was carried out in 1975, based on the standard meter. According to this measurement, the speed of light is 299,792,458 meters per second. We can say that this is the highest speed in the universe, but can we reach it? In theory, to even get close to this speed, our spacecraft would have to have no mass at all. So there's a paradox here. In order to accelerate to the speed of light, you must not exist physically. The speed of light may seem enormous, but when you take into account the distances between cosmic objects, it's not that impressive anymore. Moreover, it seems rather modest compared to human ambitions for fast travel from one point of the universe to another. Of course, light can circle the Earth 7.5 times in 1 second, but even light has its limits. When talking to a person who is 1 meter away from you, you see him 3.3 nanoseconds in the past. Actually, nothing in the universe appears to us in real time. Now, let's try to start with familiar objects like the Moon. The natural satellite of our planet is 380,000 kilometers away from its surface. And that means we see the Moon from Earth as it was 1 3/10 seconds ago, the Sun as it was 8 minutes ago, and Mars as much as 14 minutes ago. This means that it takes almost 14 minutes for the Mars rovers to make even the simplest movement because they are controlled directly from Earth. It turns out that the speed of light is a kind of limit for any other speed, radio, micro, and gamma waves. Let's try to move even further. The nearest star system is 4.3 light-years away from us, and that's the famous Alpha Centauri. There are 3 stars in the system, and the smallest one, Proxima Centauri, is the closest, 4.2 light-years from the Sun. There is a planet orbiting Proxima Centauri that is close to Earth in size. Let's imagine that it is inhabited by intelligent life forms who, like humans, are interested in observing space. So the aliens would be able to observe Earth as it was 4 years in the past. If their telescope can see every person on Earth, they would be able to see you as you were 4 years before the moment of observation. The center of our galaxy, the Milky Way, is 25,000 light-years away from the Sun, which means we see it as it was 25,000 years ago. Let's zoom out. Imagine that there is a planet 2,000 light-years away where there are also intelligent observers. To observe Earth, they would need a telescope several 100,000 kilometers in diameter. We've all seen pictures and videos of the dark night side of Earth and clearly remember the clusters of glowing dots, our cities. But 2,000 years ago there were no megacities, and it would be centuries before artificial light was invented. To see a person, you would need a telescope about 11 billion kilometers in diameter, and that's, for a second, the diameter of the solar system from the Sun to Neptune. But let's imagine that our mysterious neighbors have such technology. They would see ancient Rome and other civilizations from that distant era. By the first year of our era, Rome, whose population was somewhere between 800,000 and 1 million inhabitants, was the largest and most powerful city in the world. Most of what we know about the civilization of that ancient era is known to us from history recorded during Roman rule. The population of the Earth was about 231 million people. The most populated areas on the planet were communities founded near the Ganges, Tigris, Yangtze, Nile, and Po rivers. Do you want to go even further? The closest galaxy to us is Andromeda. It is much larger than our Milky Way, and it is believed that it will eventually collide with it. Andromeda is 2,500,000 light-years away from the Sun. We are able to observe it as it was 2.5 million years ago. An alien observer with colossal telescopes 15 trillion kilometers in diameter would not see any intelligent life on Earth at all. Humans are only just emerging as intelligent beings, learning to use tools, and are hardly aware of the great journey that lies ahead of them. It is worth noting that the aliens would be able to see not only the Earth in the past, but the entire Milky Way galaxy as it was 2.5 million years ago. These scales are breathtaking, but what if we go even further? The largest spiral galaxy, New General Catalog 6872, is located 212 million light-years away from our solar system. The diameter of the telescope would have to be truly fantastic, about 1 quadrillion kilometers or 132 light-years. So what will the observers see this time? Well, first of all, they won't see the familiar outlines of Earth's continents that we're all used to. Instead of them, there was only one supercontinent, Pangaea, which much later would split into Laurasia and Gondwana, separated by the Tethys Ocean. Both supercontinents would later break up into smaller parts, and their collisions would lead to active mountain formation. The result of Africa pressing against Europe will be the Alps, and the collision of India and Asia will create the Himalayas. Secondly, most of the Earth's inhabitants they would be able to see have long been considered extinct. The Jurassic period, the dawn of forests, abundant rainfall contributed to the spread of flora not only in the ocean but also on land. Dense forests were mainly represented by true ferns and gymnosperm plants. The class of gymnosperms, cycads, has survived to this day. Today, Jurassic representatives of flora grow in humid equatorial forests. The farther away the observers are from us, the deeper into the past of our planet they will have to look. As you understand, the same applies to us if we want to observe them. Voyager 1, a spacecraft carrying a golden record with a message for extraterrestrial life, will help us grasp the enormity of these scales. It contains greetings in 55 languages, human voices, classical music, and sounds of nature, as well as photographs of people and Earth. The record contains the coordinates of Earth and the solar system, as well as diagrams of hydrogen atom emissions. In September 2013, National Aeronautics and Space Administration announced that Voyager 1 had crossed the boundary of the solar system. It became the first spacecraft to enter interstellar space. As of today, the spacecraft is more than 20 billion kilometers away from Earth. Scientists estimate the fuel will last 10 more years, after which contact with Earth will be lost. But let's imagine that the fuel lasts for an infinitely long period of time, and Voyager 1 itself is heading straight toward Proxima Centauri. This journey would take 40,000 years, considering that the spacecraft is not moving at the speed of light, but only at a speed of 17 kilometers per second or 60,000 kilometers per hour. The vastness of space can truly be astonishing, and while the darkness of the unknown cosmos may be frightening, humanity must fearlessly seek ways to accelerate its spacecraft. Of course, if we tie our future to the exploration of other worlds. When faced with this cosmic vastness, a person realizes how little he knows about the world around him, how much there is in the world that is still unknown, things that are yet to be discovered. Why do the laws of the universe work this way and not another? Why does the very fact that we have senses seem like a mockery in the face of the distances possible in space? You can easily live without considering any of this. The world becomes understandable and orderly, but as soon as you start thinking about the incredible phenomena happening around us and far beyond the Earth, it's like the familiar walls collapse and we step beyond the ordinary. Everyone knows that the speed of light in a vacuum is the ultimate speed of any movement in the universe. This speed is almost 300,000 kilometers per second, and that's exactly how fast light particles, photons, travel. Nothing in our universe can move faster than light, because that would contradict not only the theory of relativity, but also the very laws of time. For an object that reached a speed faster than light, time would literally start running backwards. But what if I told you that there are hypothetical particles whose speed not only exceeds the speed of light, but for which, literally speaking, time flows backwards? Moreover, their existence actually fits within the special theory of relativity, rather than contradicting it. How is that possible? Let's find out today. So, we're going to talk about tachyons, hypothetical particles that have the ability to travel faster than the speed of light. The very possibility of the existence of such particles was first proposed by Robert Ehrlich and Arnold Sommerfeld independently of each other. The term tachyon itself comes from the Greek language, where tachy means fast, and it was proposed by Gerald Feinberg in 1967. The theory of tachyons has its own terminology. For example, particles that move at speeds lower than the speed of light, that is, all particles in our universe except photons, are called tardions. Photons in this theory are called luxons. So where did the very hypothesis about the possibility of tachyon existence come from? The thing is, in natural sciences, people often think in terms of the opposite. Is it possible to prove that tachyons do not exist? No. But how can they exist if it contradicts the theory of relativity and common sense in general? As we know, objects that have mass cannot move at the speed of light. Why does this happen? Remember the famous formula. E equals m times c squared? This formula from the theory of relativity connects the energy required for motion with the mass and speed of an object. So, for something with mass to reach the speed of light, the energy required would have to approach infinity, which would create a lot of paradoxes. The only particles in the universe that can travel at the speed of light are, of course, light itself, whose photons have no mass. But how could tachyons, even hypothetically, exceed the speed of light if the only particles that reach the maximum speed in the universe are those that have no mass? If photons have zero mass, does that mean tachyons have negative mass? It sounds unbelievable, but that's exactly the direction scientists are thinking in. They suggested that tachyons might have what's called imaginary mass. What does that mean? Literally, imaginary mass is the degree or measure of how much matter slows down, not acceleration as we're usually used to. To travel faster than the speed of light, you need to introduce the concept of negative inertia. This is where the tachyon comes in with its imaginary mass. This mass doesn't slow the particle down, but on the contrary, accelerates it. That's why the tachyon's faster than light speed can be partially explained by its imaginary mass. The oddities of tachyons don't end there. If ordinary normal particles accelerate when they gain energy and slow down when they lose it, with tachyons it's the opposite. They should slow down as they gain energy and speed up when they lose it. This leads to the problem of charged tachyons, because charged particles moving at superluminal speeds emit energy in the form of Cherenkov radiation. It's also called Vavilov-Cherenkov radiation. Charged tachyons would lose energy even in a vacuum and would move faster and faster, reaching speeds impossible for any kind of analysis, let alone optical perception. Simply put, when a tachyon flies through matter, it loses energy because it collides with atoms. But as it loses energy, it accelerates, which makes the collisions even stronger and happen more often. In theory, these collisions should cause further energy loss and consequently further acceleration. A vicious cycle arises and the tachyon naturally gains infinite speed on its own. It's practically a perpetual motion machine inside the particle itself. Do you think that's the end of the list of tachyons' impossibilities? Not even close. In 1970, astrophysicist Gregory Benford and his colleagues pointed out that the existence of tachyons is a direct path to acknowledging the existence of a time paradox. This concerns whether these particles can send information to the past. The very idea of sending messages backward in time appeared in physics as early as 1907. When Albert Einstein put forward the theory that if you exceed the speed of light, you can send a message into the past. But Benford developed this theory using tachyons. He presented it to the public as a playful story about Alice and Bob. Let's suppose Alice and Bob made an agreement. Alice will send Bob a message at 3 o'clock if she doesn't receive a message from him at 1 o'clock. After receiving a message from Alice at 2 o'clock, Bob immediately sends a message to Alice into the past so that she receives it at 1 o'clock. But the second exchange of messages will only take place if the first exchange does not happen. Gregory Benford called the hypothetical communication device between Alice and Bob a tachyonic anti-telephone. If the existence of tachyons is proven, can you imagine what incredible possibilities this will open up for humanity? The tachyon is a frequent guest in science fiction. In the immortal science fiction novel by Frank Herbert, Dune, there is a tachyon network that allows for instant communication and even control of particles in the universe. Tachyons play a major role in the plot of the television epic Star Trek. If we put science fiction aside, at the moment some physicists believe that tachyons may have existed at the time of the Big Bang, violating causality, but now they no longer exist. Moreover, tachyons may be directly connected to the Big Bang itself and to the very possibility that it happened. But how? There is a theory that before the Big Bang, the universe existed in a state of false vacuum where tachyons were present. But their presence meant that this was not the lowest energy state of the system, and therefore the system was unstable. At some moment, a tiny gap appeared in the fabric of spacetime, representing the true vacuum. The gap began to grow, forming a bubble. Outside the bubble, tachyons still existed, but inside it, they were gone. As the bubble grew, the universe we know appeared, a universe without tachyons. That was the Big Bang. So tachyons may exist, but somewhere outside our universe. Who knows? The search for these mysterious particles never stops for a moment, but so far it hasn't yielded any positive results. In 2011, when scientists from Conseil Européen pour la Recherche Nucléaire conducted an experiment called OPERA related to the study of neutrino oscillations, it seemed that the answer was very close. During the experiment, something incredible happened. The scientists claimed that they had discovered particles traveling faster than the speed of light. However, unfortunately, it soon turned out that the mysterious particles were not tachyons at all, but merely the result of inaccuracies and errors in the synchronization system. So, does the most mysterious of all particles really exist in nature? Will we be able to get an answer to this question in the near future? Anything is possible. Science is advancing by leaps and bounds, and much of what was once hypothetical and seemed like science fiction has eventually been proven and become an undeniable fact. One thing can be said for sure: the possibility of discovering tachyons, and most importantly, finding a way to interact with these particles. This is the path to that very future, which, for now, we can only observe on the pages of science fiction novels. What kind of budget do you think is needed to become the first space tourist on Mars? $10 billion. According to Elon Musk, with this amount, you could easily leave the bounds of our vast planet. But did you know that you have the opportunity to see the beauty of Mars and hear what it sounds like without leaving Earth? In recent years, humanity has advanced significantly. At the time this video was made, it had been just over a month since Perseverance landed on the surface of the Red Planet. And specialists from National Aeronautics and Space Administration continue to receive the information it has collected. On March 17, National Aeronautics and Space Administration released an audio recording made on March 7 using a microphone installed on the rover, and it lasts a full 16 minutes. We have already heard the sound of the Martian wind, and now we can analyze the noise made by the rover itself as it moves across Mars, where it traveled just over 27 meters. And this is really very interesting because in addition to the creaking of the rover's tracks, the recording also captured some rather curious knocks and tapping sounds. There are two versions of the recording posted on SoundCloud, the full version and a 90-second cut in which background noise has been filtered out. Listen for yourself. What do these sounds make you think of? Here we hear the Mars rover starting to move, followed by metallic tapping sounds. The tapping is audible elsewhere in the recording. And in some places you can hear a real rumble. Doesn't it sound like Martians are attacking Nastoychivost and trying to break into it? But everything is explained more simply. Many people, when they see a picture of the Mars rover, don't realize that the wheels are made of metal. When you're driving on these wheels over rocks, it's actually very noisy, commented Vandy Verma, a senior National Aeronautics and Space Administration engineer in Southern California and the driver of Perseverance. Why are the recordings from Perseverance so important to us? Perseverance is the first Mars rover that has successfully recorded and transmitted audio from Mars since previous attempts had failed. Microphones were installed on the Mars Polar Lander rover, which crashed during its landing on the surface of Mars. On the Phoenix lander, which landed successfully, electronic issues prevented recordings. But that's not all. The rover's cameras also captured a real Martian dust devil, which is another name for dust whirlwinds. We don't know its speed or height, but it's known that dust devils on Mars can reach up to 8 kilometers in height. The mechanics of their formation are the same as on Earth, and they consist of the interaction between the sun-heated surface and the cold and hot air currents above it. From space, such whirlwinds look like this. Impressive, isn't it? What do you think? Could such natural phenomena on Mars interfere with future colonization? Write your opinion in the comments. But let's get back to Perseverance. Perseverance is already making real breakthroughs, surpassing its predecessors by a head. And who knows what we will see and hear when the cameras of the drone, which is still charging and will soon begin its flight around Mars, are turned on.